Hi everyone. In this video, I'm going to be talking about the Laplace transform, which I think is a really cool piece of math that everyone needs to know. But anyways, getting to the point, this is the thing you see over here is the definition for the Laplace transform, which is represented by this squiggly looking L over here. But initially, this might seem a little weird, right? Like, what is this integral doing? Why is there an s over here? It's not immediately clear how you integrate over that s, and there's a function of two variables. It's a little complicated, but ignoring the definition and the way of computing the Laplace transform for a second, let's just look at some of the uses and what the Laplace transform actually does, and this might be able to give us some insight on you know how to do it, or what the Laplace transform actually means um, on an intuitive level. So to start off with, this is probably my favorite use case of the Laplace transform, and it is to convert between calculus to algebra. Again, it's not immediately clear how this happens, but to give you an example, consider this differential equation, just completely random. I don't know, dy dx plus y equals 0. Okay, so this is a differential equation, and I'm sure you probably have other methods of solving it. Probably like subtract 2y from both sides, then divide by y, and multiply by dx and integrate, or something, whatever method you might use. It's probably a better method in this case. But just as a just to throw it out there, the Laplace transform can actually be used to solve this differential equation. So what you would do in a typical case is just Laplace. Oh, sorry, I should write that a little bit above. Um, you Laplace transform both the sides. Now the Laplace transform of 0 is 0, so I'm just gonna leave that over there. But once you Laplace transform this expression over here, what you end up doing is sort of remove the derivative. The derivative gets transformed into something else, which we're not going to discuss over here. But I just wanted to point out that the Laplace transform can be used in differential equations to eliminate all these derivative terms and really simplify your differential equation into a regular algebraic equation that can be solved using your you know multiplying and dividing and all that stuff. Then the second use case is also pretty interesting, and it is converting from real space to frequency space. So what does that mean? Let's say I have a signal, and in this case the words signal and function, they're both interchangeable. So let's say I had a simple sound wave going something like that. So I don't know, let's say a guy just plucked a guitar string, and this is the sound wave you get as a result. What the sound wave is telling you is that at each point, this is the amplitude of the wave. So example that, I don't know, at pi maybe. Okay, so that's probably not the best thing to say since it probably has some frequency, but roughly speaking, at at different points of time, what this function is telling you is how high the wave is going, right? The amplitude. So I'm just going to put that out there. This is the amplitude and this is the time. So what happens when we Laplace transform this entire function? What we get is another function. So the Laplace transform of some function of time is going to be another function, but not of time, but of frequency. So what happens in this case is, so we know that this function has some frequency, right? I mean, it's a sine wave, it's periodic, it has some frequency. So what the Laplace transform is going to do is it's going to pick out that frequency and tell us, roughly speaking, like to a very good approximation, it's going to tell us what the frequency of this wave is. So if we Laplace transform it, I don't know, we might get something like, again, this is a very rough sketch. This is probably not how the actual Laplace transform is going to look of this function, but I'm just sketching this for understanding purposes. So probably this, I don't know, is 100 hertz, and maybe the frequency of this wave actually is 100 hertz, which corresponds to this peak over here. right? At 100 hertz, you have a peak in this frequency graph, a frequency diagram, whatever you want to call it, and that corresponds to this initial wave having a frequency of 100 hertz. So, in a nutshell, that should be telling you the purpose of the Laplace transform. It is to pick out the frequencies of a given signal and sort of, plot that. So, another way of, understanding this diagram would be, hey, at each frequency, how much of that frequency is actually present in the original signal? So, if I go really, deep down the line somewhere over here, say I keep going and, I don't know, maybe I hit 10,000. I'll just write that down. So 10,000, and there's very little of 10,000 over here. Like this is just a regular sine wave. There's nothing really crazy going on. And what the Laplace transform, the frequency diagram is telling us is that there is very little of 1,000 hertz signal in our original signal, and it looks much more like 100 hertz signal. Now, of course, there is some loss in meaning over here, since ideally, the frequency diagram should just look like a spike, should be zero everywhere, and then boom, it should spike there and go. But there are some difficulties, there are some technical difficulties, and that's why the Laplace transform gives you a very, very good approximation of what the frequency of the original signal is, but not the exact one. It won't give you a definite spike. So the reason this is useful though is, let's say you have I don't know, a guy playing a real guitar, not this imaginary little wave we've done over here. If if this was a real piece of music, that would be quite boring. But let's say we have a really somewhat more interesting piece of sound wave, and real sound waves are pretty crazy. They might look something like that, and they decay over time, as the sound gets shallower and shallower, and boom, some really weird stuff happens over here. But what we do is we make a computer do all of these, this transformation business and all that. And finally, what we'd get is, again, the frequency of, how much of each frequency is present in this initial signal. So, again, completely random. I'm just drawing something. Maybe that is our, maybe, oh, sorry, looks like I erased it over there. Maybe that's what we get after doing the Laplace transform. And what that tells you is, this signal looks like it has a lot of this frequency over here, right? And let's call that F1. And it has a lot of this frequency over here, F2. And it has a little bit of these frequencies in the middle, like, those which are less than F1. And in a nutshell, that, again, that tells you what the Laplace transform does. It serves two interesting purposes: to convert between calculus and algebra, and the second use case is to convert between real space and frequency space for signals. And in the next video, let's actually go into computing a few Laplace transform using this integral definition which I showed in the beginning. Yeah, let's actually use this guy to compute a few Laplace transforms of a few common functions, and see what comes out.